The thing about the compression world is we use them in so many different ways these days, and really very, very little content is actually done purely uncompressed these days. I mean, we get some audio certainly, but increasingly compression and other kinds of media transformations are pretty much a given in some sort of digital way. So the next one here is about kind of the opposite end of this, about optimization for make an existing codec look better or look faster, or all that kind of stuff here. So Pradeep and Alex, when you come up here while I do your introductions here. Pradeep Ramachandran has a PhD from University of Illinois and is a principal engineer at Multicoreware, Inc. He heads the team building the open source HEVC encoder X265, contributes to open source codec projects like X264 and STAV1. This is Pradeep's first SMPTE, and let's make sure it's your first of many. Right. Yeah, come on up, Pradeep. And Alex, you want to come up too? So, Alex Giladi is a distinguished architect at Comcast. He leads an advanced technologies group and is focused on video encoding and adaptive streaming. He is actively involved in MPEG standardization and authored many widely used features of that spec. In past life, he was a contributor to X264 and is still fascinated by the power of open source. Pradeep?
Cool. Thanks for the intro, Ben. It's a pleasure to be here. It's my first time, but I can see a few familiar faces. Thank you very much for attending. This work is a collaborative work between me and some of my team members at Multicoreware, along with Alex and some of his team at Comcast. The title of the talk is Speed-Distortion Optimizations, Trade-offs in Open Source HEVC Encoding. So we will be talking about some of the trade-offs that we have explored, focusing on HEVC encoding and what that entails for real-world use cases. Okay, I think I'm preaching to the choir here, but video is important, right? And specifically, where we come into the picture here is the observation that the proliferation of UltraHD content is becoming really significant, right? So there is statistics that are talking about over 20% of internet bandwidth being focused on UltraHD, most of which is HDR. So that's where HEVC becomes very interesting as a codec. There have been some patent-related issues to HEVC, which I'm sure they will have a lot of questions over, but I'm not here to talk about that, right? I'm here to talk about the technology behind what we do with HEVC. The main technological challenge behind HEVC is that as a codec, it is significantly more complex than existing codecs that are in deployment such as AVC. So there have been notions of 2 to 5x complexity, which obviously is a significant increase to compute, but that's not the only reason why there's a significant increase to compute. We also have now adaptive bitrate streaming, which means that for every title that you're going to be encoding and streaming, you need to have different resolutions and different frame rates and possibly different bit rates. So for every title, we're already talking about a multifold increase in the complexity and the compute required for the encoder, which is going to make things a lot more difficult and for us a lot more interesting. So there is a need to have an encoder that is not just widely deployable, but also flexible. When I say widely deployable, I mean it should run on really off-the-shelf general purpose processors. I'm not talking about fancy, really niche kind of systems, just general purpose x86, ARM, PowerPC based processors on typical rack-based servers. And it should be flexible because there is no one holy grail encoder configuration. Right? So we need to be able to present the power to the user. So we want people to be able to configure and encode in whichever shape and form they want. Somebody who's going to be streaming an F1 race is going to encode very differently from somebody who's streaming Game of Thrones to somebody who's streaming a daytime soap opera. It's completely different. So the flexibility has to be provided externally and not consumed within the encoder. That's the belief that we have. So this paper makes a few key contributions. The focus of the paper is talking about X265. Right? It is a popular open source encoder which has already been deployed across multiple streaming solutions that are today prevalent. This is the first paper that comprehensively talks about the presets of X265. It has been, X265 as an open source project has been in development since 2013. We crossed 6 years this March. And it is fairly popular. There's several communities that are focusing on it. But this is the first paper that actually talks about the preset, which is our pre-wrapped existing solutions that gives a very good starting point to anybody who wants to use HEVC-based encoding. Additionally, there are a couple of two recently implemented features in X265 that we've collaborated on with some of our partners, including Comcast, where these are presented as additional features on top of the presets. These are just exemplary of some of the several such features that we actually have as part of X265 itself. So before I go into the details of what I'm going to talk about, I'm going to geek out a little bit over here. So if you lose me a little bit, it's okay. Don't worry too much about it. But I wanted to give a brief overview of HEVC encoding. HEVC in 2 minutes. Let's see what we can get there. So yeah. So we start out. Okay, I'm not having. So you start out on the left side with an input signal that comes in. Right. Simply put, the input signal is cut into multiple blocks of a certain size. We start with blocks of size 64 by 64, and we take the input size and come all the way to the bottom on the right side, which is the decoded picture buffer, which has the previous frames from which we try to predict what this frame is. So you look at the last block over there called motion compensation. So we take the motion compensation and you take a previous frame and we try to do either interprediction, which is frame to frame prediction, which is for video, obviously the highest compression possibility, and intra-prediction, which is within the frame we try to predict it. And then you come back to the blue XOR gate, that's the plus on top, where you take the predicted picture, you take the incoming picture, you do a difference. Right? And the difference is your error or your residue. And we then go through a step of transforming it. It's in the pixel domain, we go to frequency domain, you quantize it, and you send out your quantized coefficients along with your prediction information, which like a coding, entropy-based coding, which is like a run length encoding, and that gets streamed out. Simple enough, right? And additionally, you want to make sure that you get your, the picture that you sent out, you want to see what the decoder will do with it. So you go through an inverse transformation. So basically the right side, which talks about scaling and inverse transformation, filter control analysis, and some deblocking SAO filters is what the decoder is going to do with it. So you do the same thing on the encoder side, and you store it back in your decoded picture buffer so that you can use this frame to predict the next frame, and so on and so on and so on. I think everybody followed me, right? So let's carry on. So some of the key tools in HEVC, I just want to highlight what are the important ones that we actually added, so that were not we added, that were added. The first thing is that compared to the previous standard, which was AVC, which only used 16 by 16 blocks and 8 by 8 blocks, simple block partition, HEVC went on the first generation of steroids and started adding quad tree based. So an incoming frame, which is shown over there, which is let's say a 64 by 64 block of the frame, can be divided into further 4 32 by 32 partitions, each of which can further be divided into 4 16 by 16, each of which can further go into 8 by 8. Right? So this gives you a quad tree like structure, and every block can independently be chosen as whether you want to stop at 32 by 32 or at 16 by 16 or 8 by 8. And it's completely independent for each block. Okay? So this is one of the key tools that enables significant compression in HEVC compared to AVC. Now, once you have these what are called coding blocks or CUs, you then have to predict them. And for prediction, you do intra-prediction or interprediction. We don't have to get into all the details, but compared to the previous generation, it's about 2x more complex than previous generation. So once you get your coding tree units, you then go to prediction units. And then once you get your prediction units, you then get your residual. Remember the error that we showed over there in the blue XOR gate. We then have to transform them. And that uses another quad tree like partition, almost like the tree that I show over here for coding units. Transform units also go through one more. So when I say it's a little more complex than the previous generation, I'm not just pulling it, right? It really is significantly more complex. One of the things that was done as part of the standard to enable easier decoding of the significantly more standard, especially also for 4K, was that there's a feature called wavefront parallel processing, through which you can actually go to a faster decode line by line. Again, like I said, if you lost me, don't worry about it. It's just a high-level idea of what we have, right? So in the encoder, there are several trade-offs that you can explore between speed and distortion. The codec only talks about what your final set should look like, right? What your final encoded bit stream should look like, and not how to get to the final bit stream. That is completely up to the encoder. And that is where we play with X265. The more the tools you use, the slower you're going to be, but the better efficiency you're going to get. The fewer the tools you use, the worse the efficiency is going to be. Simple idea. So X265 is an open source encoder, has been developed by Multicoreware. That's me and my team in collaboration with the VideoLAN multimedia community, that's the open source community, along with several partners who have been with us right from the beginning. It's available under GPL v2. It was touted as a successor to X264, which was the most popular codec for the previous standard. X265 is HEVC-based encoding, and it is optimized for general purpose. Right? We have optimizations for even the newer generation of Intel-based x86 processors, that's AVX 512-based optimizations. We implement literally every tool in the standard, right? Everything that gives you 0.01% is probably already in X265 over the last 6 years. Basically because in general, it might give you 0.01%, but it's possible that in some weird use case, which is very important for a customer, it could be significant. So it's all there, it's all controllable, completely configured. We have north of 400 options that you can completely configure. And we also do decoder compliance, which is an important constraint for any encoder. So I'm going to quickly run over 3 slides talking about different types of controls that we have. First is trying to control the shapes of the partitions. Remember, we spoke already about this, where you do your coding units, your prediction units, and your transform units. So we have a quad-tree-based structure. Remember, we have the CUs, PUs, and TUs, right? So we want to be able to control how many of these do you actually want to search. For example, do you want to use 64 by 64 all the way to 8 by 8? Or do you say, I don't care about 8 by 8, I only want to do till 16 by 16. So your coding unit control options that your CTU and min CTU actually enable you to do that. And then we enable prediction unit control. There are several prediction modes that I had shown earlier. A couple of them which are newly introduced are asymmetric and rectangular partitions. You can control those out as well. And then you can decide to what depth in the transform unit tree you want to go. Similarly, similar idea as controlling your coding unit tree. Second component, second category of features that are implemented is to control how much motion search you do. So motion search or motion estimation is very, very important for video because that is really what enables the highest percentage of compression that you can get from video. But it is also the most compute intensive component. So it's a really traditional trade-off, performance versus complexity. The more motion search you do, the better you're going to get compression. So X265 presents, again, several options. You can choose what algorithm you want to use. You want to use full motion search or diamond motion search, star motion search, successive elimination, all kinds of algorithmic options. How much you want to search, that is the range of your search. Do you want to search only 3 pixels, 50 pixels, 200 pixels, completely up to the user. And you can also do refinement for half and quarter pixels that the standard supports, and those are also configurable. You can say, I'm doing 180p content, I don't have to do quarter pixel refinement, and that's not necessary anymore. The fundamental of any encoder, which is the final set of options I'll talk to you about, is what's called the rate distortion optimization. Right? So RDO, as what it is touted, is basically trying to figure out how do you make sure that for a given distortion, you use minimum bits. Or put the other way, for a given bit rate, let's say you want to get 10 megabits per second of UltraHD, how do I get maximum quality? Right? So the trade-off between distortion and rate is the fundamental of any encoder. And RD level as an option exposes multiple algorithms for RDO. RD level is configurable from a number of 0 to 6. And on the one side, it uses complete entropy coding as part of the RDO. So it becomes really, really complex, but gives you the best looking video and at the lowest bits. On the other side, it's very simplistic, very simple heuristic, gives you the worst looking video, but is really fast. And there are several additional algorithms that control the RD level feature on top of this. Right? I'm not going to go into every single one here. Like I said, there are like 400 odd features. This is a small subset that I'm showing over here. It looks all confusing. So if I told you, yeah, you can configure my encoder, you'll come back to me and say, hey, there are 400 options. What do I choose? Even I wouldn't know, to be honest. Right? So what we do is we package them into what we call presets. So X265, inspired by the X264 configurations, supports 10 presets, all the way from ultra-fast to very slow. Very slow is our best quality. That's our flagship that's used for OTT streaming. Ultra-fast is our fastest. That is targeting more like a live use case. And so in this paper, compared to some of the other papers that we have published and that's come from the community, we focus all our evaluations on 4K HDR real-world content, primarily with very slow presets, but some of the results are with other presets as well. So we're not looking at other resolutions because 4K HDR seems to be the most popular use case for HEVC. So this graph here shows on the x-axis our speed, frames per second, FPS, relative to very slow. And y-axis shows the metric called BD rate, which is basically how much more bits. So if BD rate is positive, it says how many more bits do I need to get the same quality measured in PSNR. So for example, if your very slow is reference, so it's 1.0 FPS and 0 BD rate, ultra fast on the right extreme is 30 times slower but it's 30 times slower and takes 40% more bits. So if you're looking at a use case which is needs significant speed up, you can go to ultra fast. So medium is the use case which is in the middle, and that's typically our default preset that we use. So Alex will then continue next talking about some of the other features focusing on adaptive speedups.
Thank you, Pradeep. And now to something completely different. Presets are static. You apply the same options to all of the sequence, to every single CTU in the sequence. In case of adaptive speedups, you are trying to apply something to either a subset of frames or even something smaller and content dependent. So there are several examples of this. In this talk, we'll concentrate on two: selective SAO and dynamic RD. And this sounds cryptic, but we'll get to this in the next slide. And for now, you can use it easily at home, just adding a next parameter. So here is an example for dynamic RD. And this is available in ffmpeg. Please use it at home. So SAO, sample adaptive offset. This is one of the filters introduced in HEVC. And it was introduced specifically to address ringing. Ringing is a pretty annoying artifact that sometimes is caused by larger transforms which exist in HEVC. So from literature, it's known to be beneficial for p-frames. And right now, there is a way of turning it on or off. Obviously, it's implemented in X265 for years. And the question we asked was, what if we only enable it for a subset of frames? And the reason is very simple. Let's speed things up and try not to lose quality. So there are several options for completeness. There is an option of turning it off and turning it on. But then let's try enabling it only for iframes, only for INP, only for reference frames, and for all frames. So the result is interesting. Without looking too much into the numbers, you can get the same quality as full SAO if you only run on INP frames. You actually don't really gain much from running on B frames, and this gives you 40% gain. To be more precise, 40% gain in the time it takes you to do SAO. Then dynamically controlled RDO. The idea here is what if we go and modify the way we do rate distortion depending on both the amount of bits that we can spend and the complexity of this specific spatial area. So a little bit going on a tangent. There is a concept of HRD in AVC and HEVC, same as VBV and MPEG-2. You have hypothetical decoder that works on a buffer, a CPB-coded picture buffer. And this buffer, if you look at it from the encoder side, once you are done encoding a picture, you put the bits into it, and you drain this buffer at a constant rate. Both can be specified through command line or inferred from the profile and level. Now, there are two different rate control modes in X265. There is CRF, which is a fairly efficient constant quality mode that does not constrain the bitrate. There is the VBV mode that constrains the bitrate within the boundaries of the HRD. Now, you can combine them and get to a pretty efficient capped VBR encoding. Now, it actually works as a CRF until you get to a point where you are a little bit close to the fullness of the buffer when you are switching to the other mode. Now, if you think about it, in many simple sequences, you're actually pretty low on the buffer, and you can pay a percent or two in your BD rate, in your compression efficiency, in order to run faster. Running faster saves you either power or time or money if you are on public cloud. Then, if you are getting dangerously close to the buffer border, every single bit you can save is a godsend gift. So then you can go and pay with the cycles that you will spend, and go and use something that is more complex. And even in this case, if you end up being in a simple area of the same picture, you can go and use lower complexity and still get some cycles. So what do we actually do here? In case of buffer being dangerously full, we go and raise the RD level for complex areas being defined as by their variance. If there is low complexity, and if we don't have pressure in terms of CPB fullness, we go down and use simpler algorithms, and Pradeep already covered them. Let's say when you are doing rate distortion and you are trying to minimize the cost, you can use either some simple estimate as a model of how many bits would it take to encode something, or you can actually do an encode and use a far more precise result. And again, here is the result, and you can look at it in two different ways. One, given an RD level, enabling this dynamic control will get you to a much better quality at a small penalty of 8 to 10% of your encoding speed. And better quality here is defined as 1.2 to 1.4%. So this is the famous BD rate when you're drawing two different rate distortion curves and trying to see how much have you improved, or by how much did you make the quality worse. A catchier way of looking at it is this is a 35% gain at a negligible cost in quality. How did we measure this? We took our RD4, which is nearly the best mode, and used a dynamic RD2, which is something that is the fastest option of getting the best quality here. And we looked at the gains: 3.26 FPS in slower preset using dynamic RD versus more or less same quality, 2.4 FPS using RD6, which is the best rate distortion mode. So this is it, and a couple of conclusions and thoughts about the future. So first of all, HEVC is popular, and X265 is gaining popularity as a result of this. And the main use case for now seems to be more UltraHD than HD. And we need to go and optimize for this. Why do we care about complexity for 4K? It takes right now, if you don't parallelize and don't do interesting stuff, about 40 hours to encode a 4K asset. This is a lot of time, a lot of CPU, and is expensive. So we have different trade-offs implemented in X265 to go and arrive at a desired quality at a desired cost. Then we can go and further optimize this with adaptive speedups. Adaptive speed up right now are not included in any preset, but it's probably something that is worth considering as there is more experience with them in the wider community. So X265 is an open source encoder. It is open for contributions. Please help out and improve the quality. And in order to do that, we're organizing a grand challenge at the next MMSys conference in June 2020. And the goal is to algorithmically improve the slower presets of X265. We don't care how fast it is, but we want to see an algorithmic improvement. And obviously, there are prizes for first and second place, as long as there is an open source patch and a technical paper explaining why and how this works. So this is it, and we have 4.5 minutes for Q&A.
Any questions? Yeah. All right, I wonder if you got some. I thought a thing that doesn't get talked about a lot, but you really brought home here is that people talk about, oh, this next video codec is 7.5 times slower to encode than some other one. And, you know, I mean, even you see a 30-to-1 swing in different presets inside X265. It's really kind of a question about, you know, what kind of efficiency at a given quality level you get, at a different time level you can get, and that kind of stuff. And you can really do an enormous amount to like try to get as best quality as you can within a limited amount of processing time and the best possible quality, more unbound processing time. When you're looking at potentially other codecs, well, actually, here's a good question for you. If you're encoding at the same speed as say X264 is very slow, how much slower or faster could X265 get the be able to get a similar quality at, or how much more quality could it get at a similar encoding time?
So your question, if I understand you're saying, is if you're running at the same speed as previous generation codec.
Right, if you're running at like, you know, 24 frames a second for 1080p or whatever net, you know, what kind of quality you can get out of the same amount of time to encode both, say 1080p with X264 and X265?
I don't have a number off the top of my head. The only thing I can say is it's extremely resolution dependent, but I don't have a number off the top of my head. Maybe Alex from experiments, maybe you guys have experience there.
I don't have a good number for you either. It's worth taking a specific system and actually measuring it. But X264 is darn fast, and it has been optimized for more than 10 years.
Yeah, I did some testing on this. There certainly is, with enough cores and good enough sim, to a point where even at the encoding time, X265 at 1080p and above could definitely beat X264 at the same speed there. So even when you compare the performance and quality of different generations, it's kind of always important to keep looking at, you know, what is the quality given performance level, or what's the performance required for a given quality level there. And newer codecs can often give you better quality, somewhat improved quality at the same performance, as well as way better improved quality at way more performance.
Yeah, so that's one thing I just want to add to that, right? Even when you make a comparison like this, one thing to remember is that especially if you're doing streaming-based use cases, your encoding is only once. So even if you are, say, 2x slower, if you end up saving 30% bitrate, which is typically what we have seen across the board, across different resolutions, it's worth the 2x slowdown, because you're going to save every time you stream without 30% bandwidth, which is the biggest bill anyways. It's not the bill for the compute, but it's the bill for the bandwidth, which is the biggest. So even if you're slower, your point is very valid, you should be making a comparison at ISO speed, but even if you're slower, in the long run, the bandwidth savings outweigh the cost in compute.
There is not only the issue of bandwidth savings, you can always look at this from the compression efficiency standpoint. You can use the same bandwidth, but provide your customer with much higher quality, which is one of the ultimate goals of providing them with video.
That's a good point.
Yeah, like doing 1080p at 720p bandwidth, which was sort of, you know, we moved to HEVC. A lot of cases we were delivering 4K HEVC and 1080p H.264 bandwidths. So just because it's more efficient at higher sizes.
Significant saving.
Yeah. All right. So let's do any more questions here. Let's move on to our last thing. Thank you, gentlemen.